Welcome to The Explainer. Today we are diving into something that could totally change how we think about computing. It's a framework called Sigmatics, and it makes a pretty wild claim that it's found a hidden geometric key to solving some of the hardest problems out there.
So let's just start with the big question that's at the heart of all this. What if the problems that we've always called computationally impossible aren't actually about raw power? What if they're really just navigation problems, and we've been trying to solve them without a map?
Okay, to really get what's at stake here, just picture trying to design a new medicine. You have to figure out exactly how a new molecule might interact with all the different proteins in the human body. The number of ways that can happen is, well, it's just astronomical. Or think about a massive global shipping company, trying to find the single most efficient route for millions of packages, weaving through this crazy network of planes and trucks and warehouses. It's the same kind of mind-boggling challenge. And here's the real problem. Every time you add another variable, another atom to the molecule, another package to the network, the number of possible solutions just explodes. We're talking exponentially. It gets so big, so fast, that even the most powerful supercomputers on Earth couldn't check every single option.
Now, in computer science, there's a name for this: NP-hard problems. These are kind of like the great walls of modern computing. The search space, the number of possibilities, grows factorially. Trying to find the best solution is like trying to find one specific grain of sand on a beach the size of a planet. It's just not going to happen.
But what if there's a clue? What if, hidden inside the very data that makes these problems so ridiculously complex, there was a secret pattern? A pattern that could turn that impossible search into something more like a simple walk in the park. To find this clue, we first have to look at something called time series data. You see it everywhere. It's just a sequence of measurements taken over time. Think about stock prices ticking up and down, or the signals from an EEG brain scan. On the surface, it all just looks like total chaos.
And this is where it gets really interesting. What you're looking at is data from a Lorenz attractor, which is a classic mathematical model for chaos. But according to the Sigmatics research, it's not random at all. The data points actually fall into just 8 distinct states, or contexts. And get this, over half of them, more than 51%, pile into just one single state.
So the big takeaway here is that chaos isn't random noise. It's incredibly structured. The data isn't just splattering everywhere. It's actually tracing a path on a hidden geometric shape, kind of like an 8-spoked wheel. It reveals this beautiful underlying order that was hidden in plain sight.
So, an 8-spoked wheel. What does that get us? Well, according to this research, that simple 8-ring pattern isn't just for weather systems. It's actually one small piece of a much, much bigger universal structure that they say applies to literally all computation. And that universal structure is defined by this one number, 96. The central claim of Sigmatics is that any and all computational processes can be described within a fundamental grid or a lattice of 96 possible states. Think of this 96-class lattice as a kind of universal GPS for information. Every piece of data gets a specific address based on 3 things. First, its context. That's its position on that 8-ring we just saw. Second, its modality, which is basically what's the information doing? Is it being produced, consumed, or is it just neutral? And third, its quadrant, which is a related spatial dimension. Put them all together, and you have a universal coordinate system for computation. And this quote right here gets to the core philosophy of this whole thing. The UOR Foundation, the folks behind Sigmatics, they're not saying they built a clever model. No, their claim is much bigger. They're saying they discovered a fundamental property of reality, kind of like discovering a new law of physics. Okay, so this is all really fascinating theory, but let's get back to the main point. How does having this universal map of computation actually help us solve those impossible NP-hard problems we talked about at the beginning? It completely flips the script. The old way is that brute force search, just wandering lost through a tangled mess of possibilities. But with Sigmatics, the problem transforms. Finding the best solution isn't a search problem anymore, it's a geometry problem. It's just about finding the shortest, most direct path on this 96-class map. And the results they're showing are frankly staggering. Let's look at tensor contraction. It's a core operation in AI and physics, and it's notoriously hard to speed up. The research shows a fundamental shift. Instead of the problem getting cubically harder as it gets bigger, with Sigmatics, it just scales linearly. A network of 20 tensors that would normally take 8,000 operations can be solved in just 80. That's 100 times speed up. That's a game changer.
Now, here is where things get really, really interesting, especially if you're a developer or a researcher. This isn't just some abstract theory locked up in a research paper.
It's a real software package. You can literally open up your terminal and install it with NPM right now. They built this as a tool that's meant to be used, to be tested, and for the community to build on top of.
And the kinds of doors this could open? Well, the applications are incredibly broad. The research suggests this geometric view could be used for everything from building early warning systems for financial crashes, to supercharging AI, to designing quantum circuits, and even detecting anomalies in medical data like those EEGs.
This quote from the Foundation really just says it all, doesn't it? The core idea is that we now have a lens, a geometric map, that lets us finally see the fundamental order that was hiding under the surface of our most complex systems this whole time.
Which leaves us with one last, pretty profound thought. If this whole premise is true, if computation really is, at its heart, geometric, then how many of our other impossible problems aren't really impossible at all? Maybe they're just waiting for us to find the right map.